Okay, so let's talk about those multi-way trees. Now we've seen like binary search trees and AVL trees, and the difference between the two is, I'm sorry? The AVL is balanced and the binary search tree is not? Is that the difference?
Maybe it could be balanced or not.
The binary search tree might be balanced or not balanced, and the AVL is balanced. That's the main difference between the two? Not sure? Well, yes, that's the main difference. Well, the AVL, the main objective of the AVL is to be balanced. It's a binary search that is balanced. But it's balanced because we would like to make it, I mean, that's an objective, is to make it balanced. So it has to be balanced. But why do we use the trees anyways? To represent data? Why? Why are we using trees than to represent data? We had arrays, we were happy with those.
No, because it has a specific corridor to when I look for something, search for information.
So it's mainly about search, increasing search speed, right? So with the trees, when we organize the data, even though the implementation of some trees were using arrays, but the way we put them in array will make it easy for us to try to find out the information quite quickly. So the speed is the main thing. Now the multi-way trees are going to handle some kind of speed problems, but kind of different type of problems that happens with speed. Now the problems that these multi-way trees are handling are related to the hard disk. Why the hard disk? Well, basically when you have now a lot of data that is stored, like think about a database. Now we have a lot of information stored, and every time that you're going to look for it, it's not going to be in the memory. Now when we were adding some nodes, it's like this small number of nodes, everything is in the RAM. In the RAM everything is faster, so no big deal, it's fine. But now when the tree becomes maybe larger and the RAM cannot hold all that information, so we have to deal with this with the hard disk now, with the secondary storage. Now dealing with the hard disk is a very problematic issue. Why? Because that's the slowest thing that is on your computer or any device that you have. The slowest thing is your hard disk. Everything else is faster. The rest is kind of, I mean, okay, or depending on what type of technology they use. But the slowest thing in your computer is the hard disk. Now that's why many now hard disks have been replaced with SSDs, which is way faster. But still, they're still smaller, they're still slower as compared to the CPU. Because who needs this? Who deals with the storage? The CPU, because the CPU needs to take some information, process it, and do something with it. So mainly the CPU is just waiting. So it does something and then it keeps waiting, does something and then keeps waiting, except the waiting is very long because the CPU is quite fast. Its speed is in nanoseconds, while the CPU, the storage speed is in milliseconds, which is it's 1 million times faster, 1 million times slower than the CPU, 1 million times. Can you imagine that? 1 million times. Which means now you can do 1 million operations, and I'm just waiting for this information to come. Because so the CPU most of the time is just wasting time. So we need to find a way how to deal with those. Now what's the problem with the trees and the hard disk? The thing is now everything, as you may know, the hard disk is organized in blocks. I mean, let me see here. Now this is, they find a way to, even though they try to make this hard disk faster, and they did some amazing job just to make this slowest device less slow. Well, first of all, as you can see, they don't put just one disk. The hard disk is not just one disk, but many disks actually, and they call them platters. So we can have like 4, 8, whatever. And on each one of those platters, maybe I can use some kind of help from Google here. So a hard disk platters, and let me see maybe some pictures. Yeah. Now this is maybe an example. Yeah, and as you can see, you can stack a lot of them up together, and the idea behind that is, now how does this work? Well, on each one of these platters, like the small, this is one of these disks. The platter is a disk. This disk has a reading or writing head. Now the head is on both sides of the platter, on the top and on the bottom. So for example, if you have like these 3 platters, you have 6 heads, each one on the top and the bottom. And if you write something, now if you imagine that you have like this, let me just go to my, oh, I did not open it. Now if you'd like to write something on, I'm looking for this. If you write something on disk, now imagine that this is the disk and this is the other one below it and this is another one below it. So if you write something on the disk, it's not just writing on one platter, in one place here. This is where it stores the information. Now to make it faster, it stores on vertically on all the different platters on each face of it to store the information. Like I said, they want to store like this amount of data while they start the first part here and the second part down and the other part here and the second one down on the second part and the other part here. So basically it's like a cylinder if you look at it, because it turns and then it stores the information like vertically. So when you read something, you read all the heads are reading at the same time. So that makes it faster. But yet after all these things and all the management of these heads, storing and reading and writing at the same time, this is still the slowest thing in your computer. So imagine if at the time they were not using that, just one head, one platter, that would have been amazing. These were amazing years. But anyways, you get the point that this thing, even though they used a lot of different kind of ways how to organize that, but they just operate slower than the computer. And then they organize this into tracks. The track is if the head doesn't move and the platter moves, that's the track. So they organize the disk into tracks and each track into clusters, like a smaller apart. And each cluster has a sector and they have like some kind of, it's a block of data. Now when you probably, let me show you that. When you organize, I'm just going off topic a little bit, but I just would like to show you something interesting. Now, I don't know if I should do that, but let me just right click and format. How about that? Well, yeah, I'm just going to, I'd like to just, I'm not going to format, I'm not crazy, but I'd like to show you something. This here, when you format, generally you probably you formatted a USB or whatever. We used to format, floppy disks, but I'm not sure that if you had this kind of experience with the floppy disk. But anyways, you know what a floppy disk is?
Yeah, I know. I don't
Yeah.
remember like what.
Yeah, floppy disk. These were our USBs.
That USB.
Floppy disk. These were our USB. This is the latest one, and I didn't ever use this one, but I saw that one.
The one.
Now the size, as you can see, is kind of big. Maybe if this gives you an idea. The size, the ruler here is, I don't know, is it centimeters or inches? It looks like inches. Anyways, it's an 8-inch long.
20 centimeters or something.
So 8 inches, how many in centimeters?
20 or something. 20.
20 centimeters, like a ruler, a big ruler. That was our USB, and you have to deal with it and bring it with you. And that was, and I mean, at the time, that was, I don't know how, what's the capacity of this? It will be amazing if you just, it will be, I mean, interesting if you can see that. 12 megabit? No, I don't know how, what's the size of these floppy disks. Okay, I don't have that. Okay, floppy disk capacity. Now this 1.44 megabytes. These are the smallest one. This was the new technology. You can have 1 megabyte and a half almost stored in those. I mean, these ones, the floppy disk. This smaller one, which is smaller, and then a lot of storage. Now these ones was, I mean, I don't know exactly, but this average one is 160 kilobytes.
You can like view pictures then.
Well, of course, at the time the pictures were not like that. I mean, detailed. So as you've maybe seen, I mean, they was working with like, yeah, it was a revolution to have an 8-bit video game. The 8-bit video games, when you have everything is a cube, and that was amazing thing. But anyways, now why are we talking about that? I don't know how we forked into that. But anyways, now we would like to store things, and when we read something, we need to count how much time it takes us to read that information, and they call that, I mean, the seek time, because you have to find the place in the disk. And by the way, those were disks, and some of them were only having one side or two sides. Now they added they added two sides later on. And then the seek thing is that it has to find the place where to read, because if you would like to read some kind of information, the information has an address. Now it's like you have like, I mean, I'm going to represent this as a big block. Maybe let's empty this. Imagine that this is my hard disk. It's a set of space when I can put things. It's organized into different kind of sectors, and they have like different kind of blocks of information, but each block has an address. Let's say like an array, this is block 0, block 1, block 2, block 3, and so on. A number. Now, when you'd like to seek something, to find some data to read, let's say I have some data to read in this place. So first of all, the head, when this thing turns, the platters are turning, and the head has to position itself at that address. Then it reads. Then it transfers that to the CPU. So the seek, this is when the mechanical moving of the disk to position to the correct track. So we can find itself just on the track, which part, because it just goes up and down, so it needs to find itself which track it's going to be in. Then it needs to rotate the disk to find the correct position. Then it sends the information. So the access time is the seek time plus the rotational, the time it takes to rotate, and then the transfer time. And this is in milliseconds, while the CPU is 1 million times faster. So basically, when you store a lot of things in the hard disk, even if your binary search tree or your AVL or whatever tree you have is kind of very fast to find, it still takes a lot of time to get the information, because especially if you have a lot of data, not everything is in the RAM. So they tried to come up with another way how to do that. So they said, okay, this is not the problem. Imagine that you have a tree like this, but then this is in a block, this is another block, this is another place in the hard disk. So it will take ages to benefit from. So you waste the benefit now. So we need to find a way how, instead of having something like this, we have a lot of different kind of nodes separated in different blocks in the hard disk. Well, they said, you know what? I'm going to make a node to be the size of a block. And I remember now we're talking about the hard disk, the floppy disk, because we were talking about this thing. Now what is this thing here? This allocating unit. Now the size of a block is this. When you format a hard disk or a USB, by default it just puts this as an allocation unit. What does this mean, allocation unit? That means your hard disk is like, let's say, this sheet here, a big place when you put things. But what's the size of this thing here? The size of this is the selection that you have here. So if you say 4096, that's exactly 4 kilobytes. 4096 is 4 multiplied by 1024. That gives you this number, right? 4 times 4, 16. That's the 6. 4 times 2, 8. Plus that 1, that's the 9. And then 4 times 0, 4 times 1. So that's 4096 is 4 times 1K. But you can change that to something bigger, or, well, that's the smallest you can have. But in some other operating systems you can go down to 512, maybe half of a K.
So if I make it bigger, it's already faster.
Now let's just try to understand. I mean, I'm going all way off topic, but what's the advantage of, okay, what's the effect of choosing that? Now let me show you this. Because this is the size. Now if you store just 1 byte or 2 bytes, I'm talking about bytes, not kilobytes. 1 byte or 2 or 3 or 4 or up to 4 kilobytes is going to take 1 block. So even if you have like a small file that takes, let's have a look at my disk here. Let's have a look at some of these files. Let's just open one of them. Now all of these I have 700 kilobytes. That's a lot of 4K blocks. But let's see if I have some kind of sometimes I have something that is 1 kilobyte. This 1 kilobyte. So this thing, these two files, let's say this is the block, this is my block, this 4K block. They just fill this place, and the other place is empty. But it's still reserved only for that file, because the smallest unit that you can store in has 4K, 4 kilobytes. So the advantage is that if you increase the size, if you have big files, they take a less number of blocks. But if you have a small files, you're wasting a lot of memory. You're wasting a lot of storage, because you're going to use a big block and you store only a small portion of it. So the difference now, how can you set up, is just you have to come up with, okay, what type of files do I have? Do I have mostly big files? Do I have mostly smaller files? So that's the type of decision that you might need to take if you're dealing with kind of very optimized formatting of the hard disk. But generally we don't care about this. We just format, it's just 4K, and then we don't care about it. But that was something that needed to be taken care of, because if you see at the time we did not have a lot of storage available. And anyways, so now the idea is, now why are we talking about this thing, is that because we would like to, in these trees, instead of having like these blocks, having a lot of different kind of nodes, we will just program our tree so the full size of the block is my node. So every time if I read something, I'm just going to read the whole node, which has the whole information, which is much efficient if I have like a small node. So now the idea is that we would like to have a tree that instead of having only a node that has one value, it has more than one value. And the size of that is going to be the size basically depending on the block that we have. So that's the justification that they came up with this idea of, instead of having like a tree that we used to use with just only one value in each node, that we would like to have these multi-way trees. Now the way they work is that every node has more than one value, and there's some kind of rule that they came up with. Okay, it's a multi-way tree with an order of m. Okay, what is this m? M here is the number of children it can have. For example, what's the maximum number of children that this can have? Any node. This one, for example, how many children does it have? 1, 2, 3, 4. So this is an order M. That's why they said this M. Just how does this work? Well, basically, look at this 50. If you'd like to have all on the left side of the 50 is smaller than 50. On the right side of the 50 is between 50 and 60. So here it's between 50 and 60, as you can see. So on the left side is smaller than this part of the node, and the right side is bigger, and this right side is smaller than the next element that is on the same node, and the right side again is bigger than that one, and so on. So when we have this to be m equal 4, the maximum number of values that I can have in each node is if I said that this is the maximum is 4 here, that means the maximum number of elements that I can have in every node is 3. Because I said 4 children at max. 4 children at max, that means I have each node can have a maximum of 4 children. That means I have how many values? 1, 2, 3, because I need to have values in the middle, because every tree has a left and right. Every value has a left and right. At maximum, I can have 3 elements, what they call them keys. 3 keys per node. When m is equal to 4, so this multi-way tree of order 4, that means I have 3 keys for at max. I can have 1, 2, or 3. And yes, this tree, this multi-way tree, can be unbalanced. That's why we're going to see some another type that can just tries to not to be unbalanced, that tries to be balanced. But that's the main idea. The multi-way tree is like a tree where each node has at most m children and m minus 1 keys. This one is okay? The second thing is the keys in each node are in ascending order. The key in each node ascending. That means smaller to largest. All right. Then the other thing is the keys in the first children are smaller than the ith children. So the first children I, children are smaller than the ith children. What does this mean? Like, let's say here, this is a child of this one. This is a child of this node over here. Basically, this is smaller than any other one. If you always go left, that's the smallest. So, but there's some kind of rules that we need to. That's what's confusing about it. And the keys in the last m minus I children are larger than the ith key. Well, no, what we're talking about, I just did not explain it right. The first key in the first I child. Let's say the first child is the I is 1. That means the children are smaller than the first key. This means like this first child is smaller than this first key. The second child is smaller than the second key, and the third child is small on the third key. That's what that thing was explaining. And the keys in the last m minus I. Okay, now I is going to change. Let's say I is 1. The keys in the last m minus 1. In this case, m is what? M is equal to what?
4.
Is equal to 4. That means m minus 1.
3.
The 3. That means the key in the 3, which is the key 3, this one. The keys in the last m minus 1 children. Oh no, m minus 1 children. What is the m minus 1 children? the last m minus 1 children. This is child 1, 2, 3. M minus 1 is 3. So this is the last m minus 1 children. The last children is this value are larger than the eth key. This is larger than the eth key. Which one is the key? You got confused? Anyways, let me not go into those details because the way they're explained are confusing. But what we would like to explain is that we have, first of all, the m. M is the order, and the order is not how many numbers are in here, but how many children at maximum I can have. Okay, that's the first thing that you need to realize. So if I say in this case m is 4, that means this is how many children I can have. Every node can have at maximum 4 children. Now every key here is sorted from the smallest to the largest, and that's the thing that you need to follow. And if anything on the left of any key is smaller and anything on the right is bigger, so let's just stick to this. Don't get too much into this differentiating things, might be confusing, because now there's a lot of kind of numbers that can become a little bit confusing. A non-leaf with n keys may contain less than n plus 1 non-empty subtrees. Well, anyways, we'll go into that at some point, but for now let's just get used to just understand how these are working. Now in this type of tree, it can be resulting into some kind of unbalanced result. Now the Btrees are a type of trees that try to avoid having this kind of unbalancing. Now let me show you a Btree. That's an example. A Btree of order of 5. What does this mean, order of 5? 4 keys at max, and 5 is 5 children. Okay, you get it. And that's an example of a Btree. And a Btree is a multiway tree, but it's just working in a way that doesn't allow it to be unbalanced. And so the root is either a leaf or it has at least 2 non-empty subtrees. So at least 2. Now, for example, here, as you can see, there's no rule, it can have 1. But no, if it has 1, we don't want to allow that. We say that at least it should have 2. That's the minimum. And then each non-leaf node, other than the root, has at least m divided by 2, and this is called the ceiling non-empty trees. Well, now this needs some time. We just stop in here. First of all, what does this mean? What does this symbol mean? This symbol means
You can take it to the upper like if you have 3.5
it will become 4. Exactly. Because now if we have, for example, let's say 5 divided by 2. 5 divided by 2, that's 2.5, right? But if we do this, it becomes 3. Is the lowest integer that is greater than this number here. So this number here is 2.5. So the lowest, the smallest int that can be greater than this 2.5 is 3. So that's what this is going to give us. So basically it's kind of the opposite of, like if we do 5 divided by 2 without doing anything, int by int will give you an int 2. So this is like this representation of it. That means we just take the smallest. Now the other one is the maximum. Now let's have a look at this thing. Each non-leaf node, this is a non-leaf node, this is non-leaf node, this non-leaf node. These are leaves. each non-leaf node other than the root, that means these ones. So we're talking about non-leaf node other than the root, not the top, not the bottom. So what are these? Has at least m divided by 2, and then the ceiling of that, non-empty subtrees. Okay, in this case, m is 5. That means this 5 divided by 2 ceiling, that means is 3. Which means we'd like to have these ones to have at least 3 children, the minimum. The root can have at least 2, and the others, they can have half, a little bit more than half, than what's the size of how many children it can have. More than half, the first more than half, the first number bigger than the half of the number of children, because 5 is the number of children, this m is the number of children, and would like to have a little bit more than half of it. So that's for the non-leaves. Of course the leaves, they don't have anything, but the non-leaves, they have at least 3. So these are the rules. But actually at least 3 when m is equal to 5. What if m is equal to 4? M divided by 2, that's 2. There's nothing to do. And so we spoke about those, and the number of keys in each non-leaf node, number of keys in each non-leaf node. We're talking about these ones. Now these ones. So we're not going to allow these to a lot of empty ones. So let's check the rule. The number of keys in each non-leaf node is 1 less than the number of non-empty subtrees for that node. The number of keys is 1 less than the number of non-empty subtrees for that node. Well, that's logical, because if we say that this has 4, we cannot have like 2. You cannot have like 2 keys while you have 4 children. So what is this? So basically, if you have 4 children, you're going to be having 3 keys. If you have 3 children, 2 keys. That's obviously. Okay, I don't know why I'm going down. And all leaf nodes are the same level. And that's why we guarantee that this will never be unbalanced. And based on these conditions, the Btree is always at least half full. And it doesn't have a lot of levels, and it's balanced perfectly. Perfectly balanced means all the children have the same level. So now you can have this kind of maximum minimums in the root and in each key. This table summarizes some of that, but let's just go into this thing and try to understand how this thing work. Now, yes.
Is AVL considered a Btree?
An AVL? No, it's not. Yeah, because an AVL can have maybe not all the leaves on the same level. Just this one makes it not an AVL. And besides the fact that, well, this multiway tree means they have more than one value, and the AVL has only one value in the node. So you know what? Let's just get things practical, because I see some eyes trying to fight the sleeping, and let's try to see how this. I'm inserting something inside that tree. Now these are examples of those trees. Now all of them, as you can see, they have some kind of different type of representation, like some kind of link that goes down here, and it has something. This means null. There's nothing, empty or null, whatever. So it does not have any subtree, whatever. I mean, this is a representation of null. I don't know what this is representing then. This is empty. I don't know what kind of representation it means, but what's important is just the order. Now everything on the left is smaller than the key. Everything on the right side of that is bigger than the key, and then smaller than the other one. So all the values in between these two are between the two. So that's much easier to find like some kind of data, because you can just say, okay, is my value is smaller than this or less than between this and that, and then you can find exactly where we should go. Okay. The implementation is okay. That's a good question. Which implementation you think might be better for this type of tree? An array or a linked list? Linked list? Array?
Because we know the size.
Well, I think both of them are can be represented, but which one is the easiest into implementing? I think the array is kind of easy, because there are some rules. We know what are the maximum sizes, so I can deal with an array. It won't be easier to implement. And actually, if I remember, in the book, the implementation is shown in an array. So I mean, these Btrees are suitable for a lot of data, that can be represented, which will require less disk accesses. Anyways, I just would like to go into this kind of an example. I mean, there are different kind of cases when we would like to insert things, but let's just go for one simple case. For example, we have this here. After we insert 7, now if we insert 7, what should happen? 12 is bigger than 7, so we go to the left. And then we start here. There's 5, okay, smaller than 7. We need to be to the right of the 5. And then there's 8 to the right of the 5. So basically the 7 should be here. So what is going to happen is you put this there and you put the 7. And the thing is, when we insert inside of inside of a Btree, that's the thing. We never insert anywhere else besides a leaf. So when we'd like to insert something, we insert always in the leaf. And then we try to see if the ordering is still okay, or if we still have place to put something, and we deal with that. But for example, what if, for example, I'm inserting 6 inside here? Where does the 6 go? 6 should be here, right? But there's no more room. So what is going to happen is that I need to create another node with the same size, as you can see, and this is going to be now on the right side of the 6. But where can I put this 6? So I'm going to notice that I try to put something from the node, from the leaf, and then I'm going to try to go until make sure that my Btree is still a Btree. So now the thing is that there's no way to put inside this leaf here, so I need to split these into 2, and then the 6 is going to be put on the top, and now I'm having a Btree. And there's another case. Well, this is another case, but this is a little bit less clear, but we'll have a look at it. This is another example with this thing, when you have to insert an S. Where does the S go here? S goes here. And if you look at this thing, what's the M for this one?
2.
M is 3. Well, that's M is 3. How many children? Don't forget, M is the number of children, and that's what the confusion might come in. And because we're used to M is the number of something, but now generally we're thinking about the node, but the node is M minus 1. So now, if I have this S, this one S should be here, but there's no way, there's no place for S to be here. So what should happen? I'm just going to put S into a new node, which is going to be the leaf, and the R is going to be now the head, I mean the parent of this S. But then this is also full. So what can I do? Well, the same thing. I'm going to just have the R to be the parent of this S, and then take whatever it's the other one that was the parent before here, and becomes the parent of this R now. And now we have this one here that needs to be sorry, when I check the parent, I'm here. So I'm putting this parent, and now this should be the parent of between the N and the R, and I need to link it, but there's no more room. So what is going to happen is that now the size of the height of my tree is going to go up, because this L is going to be now the parent of these two, and the L goes to be the root. So as you can see, we always add from the leaves, and we work our way out, our way up. So I just would like to do some exercises now. I have some file that I'm going to use from what Dr. Bashir actually has prepared. I'd like to use that. Oh.